All right, hi everyone. Welcome to another lecture in the MATLAB Crash Course series. My name is Stephen Yagmore, and today we're going to be looking at for loops and iterated operations with MATLAB. So some of the topics that we're going to cover today. First and foremost, we're going to look at the purpose of the for loop and what exactly it is, why would we use it, why is it efficient to write code with. Then we're going to look at the basic structure of the for loop. Then we're going to look at using the variable of iteration, which will make more sense once we get rolling. Then we're going to calculate running totals using for loops. We're going to take a look at nested for loops and how they might be applicable in certain circumstances. Then we're going to take a look at for loops and vectors and for loops and matrices, and probably going to see a little bit why using them with vectors and matrices usually not the most efficient way. There's usually a way to write more efficient code if you want to use a for loop for a vector and matrix. But that'll make more sense as we get there. So first of all, we've got the purpose of the for loop. So far, everything that we've written in MATLAB so far has allowed us to do only a few basic operations. Essentially, we have a certain task at hand, a certain task we want to complete, but we can't do multiple of these tasks. Every time we want to complete a separate task, we need to type code for it. We have to say, okay, I want to calculate the area of a circle. Okay, if I want to calculate the area of 3 circles, I got to type 3 separate lines to calculate it. In general practice, though, whether it's data science or computation, etc., there may be hundreds of thousands of operations that need to be executed at a given time. So let's say I have all this data. Let's say I don't want to calculate just the area for 1 circle. I want to calculate the area for 500,000 circles. I can't write 500,000 lines of code. No one can write that much time. No one has the attention span. No one gets paid to do that. We can't do this. For example, how could we calculate the compound interest? Let's say a bank is watching over 2 million people. How could its user system, how could its software or hardware, how could it do anything to calculate interest for 2 million people? No one could write code to do any of this, but in virtually every single programming language, it allows for multiple iterations of the same operation to take place with just a few lines of code. The for loop specifically, which we'll see, allows for a specified number of actions to be executed in just a few lines of code. Meaning if we need 500,000 of the same action to be executed, we don't need to type 500,000 lines of code. If anything, we could type a single line of code or just a few lines of code, and MATLAB will actually do the rest for us. So let's look at the basic structure of the for loop. So right here, the block right here represents the basic structure of a for loop for MATLAB. So you'll see the keyword for is placed right here. Followed by it is a variable. I call it var it. And this is the variable of iteration. That's that word I mentioned earlier. So the variable of iteration specifically is a variable that we use to essentially keep track of which count we're on in our loop. And hopefully that'll make more sense in a second. But so we have the for, variable of iteration, and then we have the range. The range is a single vector. So you have to enter a vector here for the range. That consists of the range of values the loop will iterate through, essentially. So basically, it tells you how many times this loop is going to go through. The length of the range vector, so if we have the vector 1, 2, 3, 4, 5, the length of that vector, in other words 5, will be how many times the loop actually is run through. And then everything inside the for loop is the action or actions that are going to be specified, going to be executed. And every time this for loop runs, that action will take place. So we have the for, we have a variable of iteration, which keeps track of which number we're on. So the first time it goes through, let's say our vector is 1 through 5. The first time it goes through, this variable is 1. The second time it goes through, the variable is 2. The third time, etc., until it gets to 5, and then after then, it's going to end. What's key about the for loops, though, is it's very significant and very useful when we know how many times we want to loop through the code. When we know how many times, this is useful. When we don't know how many times, we can't use this loop, and I'm going to specify that in the next video. But if you know how many times you want to loop through it, you can just go ahead and use a for loop. And so I have an example to start out with. I've got a lot of examples we're going to look at today because this is a really key core concept in programming in general, is the for loop. But so here we have a print loop. So this script will repeat a sentence using a for loop. So we're going to use a for loop to repeat. So here I have for. I is a very common variable of iteration in almost every programming language, I, J, any of that. So if you're going to use a for loop, usually it's good practice just to use a single letter unless you want to use something else to specify, but it is up to you. So for I, variable of iteration, equals, here's our range here. This is a vector. Remember, this is the vector 1, 2, 3, 4, 5. The colon is using colon notation. So we have this vector here, and this tells us that we are going to, for every value in the vector 1, 2, 3, 4, 5, we're going to print this line. This was printed with a for loop. So let's actually see what happens if I run this. If I run it, executed, and it printed 5 times. And I only used a few lines of code to do it, which is really nice. It's like, okay, cool, so it can print a few times. Well, it can print more than just a few times. If we wanted to, we could print it 2,000 times. And a computer is a lot faster than a human at doing any of these computations, any of these calculations, any printing. So this is going to be absolutely no sweat for a computer. So let's say I run this. I say print loop. Now, you may not be able to see, but we printed it 2,000 times, and it took basically no time at all. In fact, there's the top of it. This is 2,000 times saying this was printed for a for loop, and it took like not even a half a second for the computer to do it. That's a lot more convenient than trying to sit down and type all of this 2,000 times. You saved yourself a heck of a lot of time doing all that. We could even make this, user-friendly if we wanted to. We could have the user specify how many times to loop through. So we could say n equals input, enter a number. So the user can enter a number here, and then maybe whatever number they enter is the number of times it'll loop through. So let's say we run this. Get rid of this. So it says enter a number. Let's see, let's say enter 50. It printed the for loop 50 times. You might not be able to count it, but you can see we printed it 50 times. For loops are really nice if we want to just complete some simple tasks. Now, albeit this is a very trivial task, not really necessary for anything, but you may find in a lot of your endeavors with coding that there are going to be times where you have to do a lot of the same operation. And instead of doing multiple different lines of code for it, just type a few lines of code and use a for loop. It's a very simple concept, but sometimes it's a little tricky to know where exactly you can use it and where it can come across. Generally, you want to make your code as efficient as possible. So whenever you can utilize something like a for loop, it's generally recommended to, except when we're doing vectors and matrices in MATLAB, and I'll explain that at the end. So that's the basic structure of a for loop. Now, that variable of iteration that we looked at, in that last example, you see that variable of iteration we had. Let's clear this here. Remember, we had this variable of iteration, I, right here, but this I didn't really do anything at all. It just kind of existed. N was a little more important. It was the number of times we looped through, but the I didn't do anything. However, the variable of iteration doesn't just for the purpose of keeping tabs on the looping. It can be used in calculations, and sometimes good code will use the variable of iteration to make it more efficient, or we'll use that variable of iteration, and sometimes it's necessary to. The variable of iteration can be placed inside and only inside the for statement block, and the value of the variable will change with each iteration. So if we go back to that previous example we just had here, so this I variable, this changes each time the loop goes through. The first time we go through the loop, let's do the previous example. Let's just say we're going from 1 to 5. Let's delete this here. So if we have this, our first example, the first time we go through the loop, I is 1. The second time we go through the loop, I is 2, third time I is 3, fourth time I is 4, etc., etc. Now, once again, the I isn't doing anything here, but let's say we have an example like this. Once again, this is a very basic example, but let's say we want to just print some numbers to the screen. You could say fprintf1, fprintf2, fprintf3, or we could use a for loop, but in this case, the variable of iteration is actually important. You can see here we're going to be printing numbers. It says fprintf, we have the %d, which is our placeholder, and the number we're putting in there, our integer we're putting in there is I. I is changing each time. The first time it goes through the for loop, I is 1, so the value printed is 1. The second time, I is 2, the value is 2. The third time, I is 3, the value is 3. And if we run this, you'll see that we're printing those 10 numbers right here, 1, 2, 3, all the way to 10. So in this case, we actually use the variable of iteration. Now, once again, this isn't really a calculation, but you can see there are some cases where using that variable of iteration can be useful or can be helpful in this case. The variable of iteration has to, once again, that has to only be used inside the block with the for loop in it. So if you look here, I can't print the I outside of this for loop. I can't say anything about I because I only exists in this block here. Once you leave that for loop, you can't use that I variable for anything. You can't use it before the loop, you can't use it after. Only inside this loop can you use this I variable. If I wanted to use I for anything else, I'd have to clearly specify what it equals after the for loop or before the for loop, depending on when I want to use it. Understanding the use of the variable of iteration is crucial to understanding how and when to use for loops. If you can identify a time where the variable of iteration can be important, meaning, oh, I want to loop through these values, I can use the variable of iteration, though, to help me with my calculations. That can be very crucial to knowing, hey, I can use a for loop here, or hey, I want to loop through this process instead of trying to type it so many different times. So here's an example where we'd actually use a for loop in a calculation. Let's say we're calculating the area of circles of radii 5, 10, 15, and 20. So we want to complete 4 calculations. Now, generally what we've been doing in the past is typing 4 separate blocks of code. Calculate the area with radius of 5, then calculate with area of 10, then calculate it with radius of 15, loop through and print the values. But now that we have these for loops under our belt, I have another script to show here, calc area. So this script will use a for loop to calculate the area of circles of radii 5, 10, 15, and 20. So first we start off by creating kind of a header for our table. We say areas for a circle, we have radius, and we have area. We're going to use a for loop to calculate the areas and then print those areas to the command window. But instead of doing multiple different blocks of code, or 4 different blocks, since we have 5, 10, 15, and 20, we were able to compact it all in just a few lines of code right here. But in this case, our range that we have isn't like 1 through 5 or 1 through 1,000 or anything like that. We're going from I equals 5, colon 5, colon 20. If you remember what this looks like, if you remember our little lecture on matrices and vectors and how to represent them, that's the vector 5, 10, 15, 20. So the range in this case is 5, 10, 15, 20, but it's not going to compute this 20 times. It's going to compute it 4 times because it computes it once for every element in the range, or it'll compute it the number of times equal to the size of the range vector, in this case 4. So it computes this 4 times. We say area is pi times I, so we don't say radius in this case because I is our radius. I is changing each time. The first time I is 5, and then we print to the screen. We say, okay, print what was the radius? The radius was I, because we're keeping all of our radii up here as the variable of iteration. We're not making a separate variable for radius, we're keeping all the radii in the range. Then the area is what we computed. So you can see here, we're using the variable of iteration to our advantage, storing all the radii in the variable of iteration, and then instead of putting radius equals 5 or radius equals 15, radius equals 20, instead we just use I in our calculation, because every time it goes through the loop, I will be a different value. So now if we actually run this, oops, let's see clear, we're going to say calc area. Areas for a circle, 5, 10, 15, 20, and these are our areas. So it's all rather intuitive. You have to just understand, when can I use a for loop? Why would I use a for loop? In any case, if you have to complete the same operation more than one time, there's most likely a solution with a for loop there somewhere. There's most likely a way you can do it. You just have to be maybe possibly a little intuitive to understand. All right, so now we're going to do a few examples. So example 1, create a table of sine, cosine, and tangent with input values in degrees ranging from 0 to 360 degrees in increments of 5. So if we try to completing this task without using any for loops whatsoever, this would take a long time because we're going by increments of 5 degrees and we want to get from 0 to 360. We can't compute the sine, cosine, and tangent. We can't type all that out. That's a lot of time. That's a lot of wasted time. If you're working for a company, at this point, they're going to be mad at you because you don't have it completed already. So what can we do? So I have some code to start off. I just have kind of a trig table to start. So let's be a little more specific. This script will display a table of sine, cosine, and tangent values ranging from 0 to 360 degrees. All right, so first, print header. All right, so now what are we going to do here? So now we have all of this situated, so now we should actually go and calculate what the sine, cosine, and tangent would be for all of these different angles. So what can we do? Well, in this case, we can use a for loop, most likely, because we're doing this a certain number of times, right? So what we can do here is we can say for And then let's see, what should we have our variable of iteration be? So let's just call it I in this case, but what should our range be? This is the more pressing question. So we want to go from 0 to 360, but we want to go in increments of 5. That means that we should have our lower range be 0, our step size be 5, and our final value be 360. This is going to be the best range for us because it creates a vector that contains all the degree values that we want in our calculations. And then we can use those values when we actually compute sine, cosine, and tangent. So the first thing we have to do is we have to recognize that in MATLAB, sine, cosine, and tangent must have radii, radians for input. It can't have degrees. So the first thing we're going to have to do is we're going to have to take in our for loop, whichever degree we happen to be on, the first time it'll be 0, then 5, then 10, then 15, we have to convert that to radians. So let's make a new variable rad equals, how do we convert? Well, it's going to be the degrees times pi over 180. That's going to give us a radians. Now remember, we're using I in this case, but I has a different value every time. That means every time we go through the loop, rad or radians will also have a different value every time we go through the loop. That value is changing, it's not constant. That's what's really crucial to understand about for loops is that all of these variables inside here, a lot of them are most likely going to be changing each time you go through the for loop. Something's going to happen with these. Something's going to be different about them. So we have our radians. And then what do we have to do here? So we have our radians. Now we need to actually compute the sine, cosine, and tangent. So I'm going to say V sine is going to stand for the value of sine. So we're going to say the value of sine is going to be the sine of our radians. V cosine will be the value of cosine, is the cosine of our radians. V tangent is going to be the value of the tangent, which is going to be tangent of the radians. So now we have the sine, cosine, and tangent. Now we're going to want to print these to the screen in a way that makes it very nicely formatted, nicely organized. So we have 4 different values we want to display: the angle in degrees, the sine, the cosine, and the tangent. So we're going to use fprintf so we can format. So first we want to print the angle. Let's print the angle in degrees since that's going to be what the user can most likely recognize. It'll be 0 through 360. If we do radians, it's going to be decimals. It will look bad. So I'm going to go -8%. -8d. Remember, d is for an integer value because it's 0 to 360. Those are integers. Then after that, I'm going to go 9.3f. Remember, the 0.3f means that these are decimal values, and we're going to 3 decimal points. The -9 is just for formatting. I already calculated what these should be in the first place. To know exactly what values to use for your -8 or -9 or any of that, it's most likely guess and check work. Just format it, see if it looks right or if it matches up. If it doesn't match up, try again with different values. So we have that. Then we're going to go -9.3f again for cosine, then %.3f for tangent, because once we get to tangent, it doesn't matter what it is. We have to put the -n in this case. It's really crucial that we do, because if we don't put the -n, every time it goes through the for loop, it's going to keep it all in one giant line. And we want breaks between each line. All right. So this should be, there's just one other thing we forgot. We need to enter our input arguments for this. What does the D, F, F, and F stand for? So the first one, the first placeholder, the D, will stand for the degrees, which is I, and I changes each time. Then we have V sine, V cosine, and V tangent for our other arguments. The sine, cosine, and tangent for all these will also be changing each time. It's crucial to note that. So let's see what actually happens if we run this. So we have our trig table. Let's exit out. Trig table. So here we have all our values printed out with pretty good formatting. The negative sign kind of makes it a little bit wonky, but that would be a little bit extra formatting we don't need. You see some really high values for tangent here. That's because the tangent of 90 degrees is technically, it approaches positive infinity, so we have a really big value. That is normal though. Tangent's weird like that. Sine and cosine stays between 0 and 1, and -1. So now we have ourselves a little nice reference for us if we ever need to compute and we don't have a calculator on hand. But we do have MATLAB, so that's basically a calculator. So I don't know why you'd want this, but we were able to complete it. Create a table listing the monthly balance of an individual over a year given a starting balance, a monthly deposit, and an interest rate as input. So we're dealing with input in this case. So we're actually going to do a little bit of work with functions here. Remember, functions we talked about just a little bit when we were talking about writing scripts with MATLAB, but I'm going to do a little example because knowing how to write a function, even though we're going to talk about it in more detail later, is still really crucial to understanding. So let's see. Let's do finance. Let's just call it monthly balance. So this case, we're not just dealing with a script, we're dealing with a function, meaning that when we run it, we can't just say trig table, we can't just say monthly balance, we have to say monthly balance, and then in parentheses put values in. That's what differentiates a function from a script. So we have a function in this case. Our output is actually not going to be an output in this case, technically, because we're just printing values. So we're not going to have an output. But so it's going to equal the name of our function, monthly balance. What are the values we want in here? Well, so we're going to be given a starting balance, a monthly deposit, and an interest rate. So those are going to be our three variables. We got starting balance, we got deposit is a monthly deposit, and an interest rate. So those are the three values we have to work with in this case. That means that these variables are automatically defined. It's something that the user has given to us. We don't need to say starting balance equals input, put a starting balance here. In this case, when we run it, it's being used as a function, kind of like how you use the sum function, for example. We're actually going to come back to this function in a second, but remember, this function takes a vector as an input and gives you an output. In this case, we're putting three numbers in, and in this case, we're not displaying anything, we're not getting anything out, but it is displaying something to the screen. So starting balance, deposit, and rate are three values that we automatically have at our disposal. We can use these values because we're assuming these are values that the user has given to us through the command line. So we have our starting balance, we have our deposit, we have our rate. So the question is, how are we going to create a chart that displays with every month how much our total balance is? Well, so what we can first let's say what this does. So this will display the monthly balance of an individual's account. Let's call it that. So first, print header. So fprint f. So we're just going to have two different values here. We're going to have our month, and we're going to have our total balance. Let's make it look nice. Let's add just a few equal signs here. So now what are we going to do? What we have to do is we have to, go through and calculate, okay, what's going to be the starting balance at every single point here? What's the deposit going to look like? How does the deposit play in? Let's assume for this case that we have our starting balance. What happens is we automatically go and we calculate the interest for that month, whatever it previously was, we calculate what the interest would be or what the new starting balance would be, and then we add our deposit. It's going to be as straightforward as that. So what we can do here is we're going to have a for loop for I equals. And so what's our range going to be in this case? Well, we know that this is going to be for a total of 1 year, and these are monthly deposits and monthly statements. That means we want, one loop for every month in a year, which is going to be going from 1 to 12 since there are 12 months in a year. So what are we going to do? We want to calculate what our total balance is going to be in that month. Let's say the starting balance is going to be after month 0 is going to be the starting balance. Month 1 will have the rate and deposit taken into account. So we want to say what our total balance is going to be. So we can say that our total balance is going to equal, and this is kind of segueing into what I'm going to talk about next. I believe it's one of my next slides that I have here covered. Yep, this kind of is going to segue into what we've been doing a little bit. What we're going to do in the next one, calculating running sums in this case, but this is just going to be a little intro into that. So you have total balance equals, so we're going to start with total balance equaling, what's the total balance going to equal when we start? Well, it's going to equal the starting balance. That's going to be our first total balance. That means we're going to initialize total balance as the starting balance. I'm going to talk about this in the next slide, but so hopefully it'll make a little more sense when I talk about it. So we have our total balance equals, how do we calculate what our new total balance is? Well, the new total balance is going to be the old total balance plus, it's going to be plus the total balance times our rate plus the deposit. Because we have our previous total balance, we add whatever the rate is multiplied by our total balance, and then we finish off by adding the monthly deposit we're putting in each time. That's going to give us what our total balance is. Then here we can use F for formatting, and what are we going to put here? Well, so we want to put the month value along with the total balance. So for the month, how many spaces do we want to take up? 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to take up 9 spaces, so I'm going to say -9, or I'll have to say percent, -9, D, since it is an integer value in this case, because we're dealing with I. And then for the next one, doesn't matter how much I take up, but let's go to 2 decimal points, because we're dealing with money here. So 0.2F, what are the 2 values that we have? So the first value is going to be the month, and that month is going to be either 1 through 12, which is just going to be I. And then the second value we want is going to be the total balance. And that's straightforward. Let's see what happens when we run this. But when we run this, we need to be careful. We can't just run it as normal. If we try just typing, what was the name of it? Monthly balance. If I just type monthly balance, it says not enough input arguments, because remember, this is a function. It needs 3 different values. It needs the starting balance, it needs the monthly deposit, and it needs the interest rate. So we have to say monthly balance, we need to enter 3 values. Let's say we start with $1,500. The deposit we're going to put in each month is going to be $10. The interest rate is going to be, let's do something realistic, because we've done things that aren't realistic previously. It's going to be 0.2%. Let's do that. So now that we do that, we have what appears to be here our running total of our total balance. We have the month going from 1 through 12. The first time we go through, we multiply 1,500 by 0.002 to get the interest rate that we add on. Add that 10 to it, we get, this is our first value. As we keep going through, you can see we're getting new values for our total balance each time. And what we did right here, if you look what we did right here, where we initialized a value and then we had total balance on both sides of this equation here, that goes straight into what we're talking about next, which is calculating the running total. So running total is commonly utilized in a for loop, or something that a lot of people will use for loops to calculate. A running total being we have a process that keeps happening. How does our net change or net worth or anything like that keep accumulating as we go through a process? Or as in the example we just saw, if we have a starting balance and a rate and a deposit, how does our running total or our total balance change over time or change throughout time past the months? For loops are commonly utilized to calculate the running sum or sometimes a running product. To calculate a running sum, for example, one must first initiate the sum before the loop begins. That goes back to what we did right here. We had to initialize what our starting value was before the loop began. If we just said total balance equals, if we left this out, MATLAB wouldn't know what this total balance is, and then we'd be into some trouble. So let's say we tried running the previous thing. Undefined function of variable total balance. Error. We have an error because we didn't initialize our total balance variable. Total balance equals starting balance. We need that variable for this to work properly. After deciding what value to increment by, we type sum equals sum plus the value. The value being, in our case, the value was the total balance times the interest rate plus our monthly deposit. That was our value, but the value can change depending on what your problem is. And the value of the sum is replaced after every iteration. So we say sum equals the old value of our sum plus some value. Then we get a new value for our sum. When we go through the loop again, our sum gets replaced. Basically, it's an exchange between the old sum and the new sum. Our old sum starts at 0. When we add the value, that value is our new sum. When we add that value again, we replace this sum. It's not 0 the second time through. It's whatever we got in our last iteration. Every time the iteration goes through, the value of sum keeps updating, meaning the value we add to value right here is going to change every single time, meaning that we're just incrementing, we keep gathering everything, we keep storing it, and sum just gets replaced over time until the last time sum is the final value we want. I believe I have another example where we can look at this. Running total.m. So this script asks the user for a value and will calculate the sum of all previous positive integers from 1 to that number. So the user enters a number here, And what ends up happening is MATLAB adds 1 plus 2 plus 3 plus 4 plus 5 all the way until it reaches that number the user entered, and then prints that running sum. So first we say enter a positive number. I check to see if they did enter a value greater than 1 or equal to 1. If they did not, the script automatically shuts down and says, okay, it's not going to work because it won't work anyway. Then we initialize sum starting at 0. We have to say sum equals 0 to start because when we go through, sum has to equal something to start out with. Let's say if we entered 2 in here, we just want to do 1 plus 2. When we do our for loop, we can't just start with nothing. We have to start with 0. So the first time it goes through the for loop, sum plus I is 0 plus 1. And then sum equals 1. Then the second time we go through, sum is now 1. I is 2 in this case, because that's the second time we've gone through the loop. 1 plus 2 is 3. Sum now equals 3. And then the running sum is printed. So let's actually try using this. So we're going to say running total. Enter a positive number, let's say 5. The running sum is 15, meaning 1 plus 2 plus 3 plus 4 plus 5 is 15. We can do a really big number if we want. Let's say 10,000 calculates the running total as 5,000, 5,000. Value right there. So you can see we had to initialize what our running total starting value was, saying sum equals 0, because that's the value I want to start it off as being, and then we increment it by the value each time. In this case, our value was the variable of iteration. Sometimes it might not be. Sometimes, like in the previous example, the value we're incrementing by is like maybe this entire thing here. We didn't even use I when we did it, well, until we printed it up here. But we had to still initialize our total balance as the starting balance when we started. It all depends on your problem statement. When you look at a problem and you want to code, you really need to understand what the problem is asking, what you want to start with, where you want to go, where you want to finish. All that is crucial. So let's kind of go through these a little quickly. So another topic that we have here is nested for loops. And a nested for loop is essentially what it sounds like when we say nested if statement or anything like that. It's a for loop inside of a for loop. But if any data type is arranged in a way where there's more than one variable to keep track of, nested for loops can be used to iterate through the elements. So in this case, you can see, let's say we keep something in a matrix, for example. If you want to loop through that matrix, and I actually have a slide talking about that, you have to use a nested for loop. Every time the outer for loop goes through a single iteration, the inside for loop goes through all of its iterations. And that makes sense if you think about it. Our outer for loop right here, we have our first variable of iteration, we have our first range, we have some actions possibly, but inside this for loop, we have this entire for loop here, meaning while our outer for loop is on its first iteration, this entire for loop should already be done. Then once this for loop is done, we start on the second iteration of this for loop, meaning that this inside for loop is going to be calculated not just one time, but however many times this for loop indicates, meaning that inside for loop is going to see a lot of iterations. And if we could possibly have a nested for loop inside there, we could have a third for loop inside that one. That one would go through even more times to the third power. It's all exponential. Actually, there's topics of algorithm analysis that take a look at how using for loops and nesting them changes the speed of a program, but that's not important. Believe I have an example with this here. Is it calculate, create, back, multiplicate? Believe it is multiplication table. So for an example, we could use nested for loops in creating a multiplication table, such as this. So let's say I want to make a 10 by 10 table that has all the multiplication facts in it. Basically meaning you have your rows and your columns, and the intersection of different rows and columns gives the product of that multiplication. So what we have here is we loop from 1 to 10. But then in here, we also loop from 1 to 10. Every time we reach here, we're going to print a value. And that value is going to be whatever I is times whatever j is. And then here we say if j is equal to 10, we're going to start a new row. So that makes sense. We go through, let's say we're on our first iteration. We go through iteration 1, so I equals 1. When we get through here, the values we're printing are 1 times 1, 1 times 2, 1 times 3, 1 times 4, all the way until we get to 1 times 10. Once we get to 10, then we're going to add a new row, and then we get to I equaling 2. When I equals 2, we got j equals 1 through 10. So we got 2 times 1, 2 times 2, 2 times 3. All the way, once you get to 2 times 10, we start a new line. And that repeats until I goes through all 10 of its iterations. J is going to go through 100 iterations. because it has 10 iterations, but it repeats the whole process 10 times. It has 10 by 10 iterations. So let's see what happens when we run this. So when we run it here, we create our multiplication table. We have the values 1 through 10, 1 through 10, and since we did in our statement here, we said the value we're printing is I times j. So when it goes through the loop, whatever the row is times whatever the column is going to be the value printed. So if we take the 6th row and 7th column, we get to 42, because 6 times 7 is 42. 9 times 9 is 81. 4 times 2 is 8. And that is how you multiply. Hopefully you know how to multiply at this point. But so we can use nested for loops to keep track of all this. For loops and vectors. Vectors are commonly utilized as data containers in MATLAB, as we've seen in the second or third lecture video that I've had here. So it can be rather common to loop through elements of the vector. The most common way to loop through elements, meaning let's say we want to gather the sum of the vector or anything, is using a range of 1 through the length of your vector and use the variable of iteration to index the vector. One may also want to take values and save them into a new vector. Before saving values into a vector, it is good coding practice to pre-allocate space and then utilize that space in your for loop. Pre-allocating space consists of allocating memory before the vector uses it. After pre-allocating, the values can be saved to the vector for use of later code. So there's a lot of random words thrown at you, but I have a couple examples showing this. So let's say we want to take the sum of all the elements of a vector. Now we already have a function that exists called the sum function. I mentioned that a little bit earlier, where you genuinely just put sum, you put whatever your vector is, 6, 7, 8, and it calculates the oh, I got this variable sum right here. That's the problem. I was wondering why that wasn't working. 6, 7, 8. So when we add 6, 7, 8, the sum of all those variables is 21. But if we have this here, we say add vec right here. This is essentially making our own function to add that. This is our function, remember. So the user enters a vector, and then we will calculate the sum of that, of all the elements of that vector. So first we have to initialize, we're taking a running total, so we initialize sum equals 0, and then we say for I equals 1 through the length of our vector. Because the length of the vector, like if they enter 3 elements, it'll be 3, so we go from 1 to 3, meaning we loop through 3 times. Then we say sum equals sum plus vec of I. We're using I, the variable of iteration, to index the vector and pull out a value that we want to add to our running total. So we start with 0 as a running total, then whatever the first value is, we add that to sum. Then whatever the second value is, we add to sum. Whatever the third value, we add to sum, etc., etc. So this is essentially another way of writing the sum function. So as we saw here, sum of 6, 7, 8 gave us 21. What happens if we use our function? Add vec of 6, 7, 8. Invalid expression. I forgot brackets at one point. There we go. We get 21 again. So this accomplishes the exact same thing as our sum function. So essentially, the lesson here we learned is use the sum function, don't loop through a vector. But this is just a way of demonstrating how we can loop through a vector. For loops and matrices. Nested for loops can be utilized to loop through the elements of a matrix. Before creating the for loop, one must determine the ranges in which the for loop should be iterated from. So when we want to loop through a matrix, we have rows and we have columns. That means that the best way to loop through it is by looping through it using nested for loops. We have to use nested for loops because we have rows, and for every row we have so many columns to go through. We need to use for loops inside of for loops. Here we have the way of knowing what our ranges are, because in this case we don't just have length of vector, we have 2 values, we have the rows and columns. If we use the size function for a matrix, we get R and C. R being the number of rows, C being the number of columns, and we can use those dimensions as our maximum range values for the for loops. Generally, the only action will take place inside the second for loop where both the values of R and C can be used. Let's see how this all comes out. So I have another function. Actually, before I talk about matrices, there's one other thing about vectors I wanted to talk about, and it was, where was it? Create vec. Let's say we want to create a vector instead of looping through vector. I will get back to matrices in a second. I forgot about one part here though. So let's say we want to actually create a vector. So this is a function createVec that asks the user for elements to add to a vector. This is where that pre-allocating that was talked about on the last slide came from. The pre-allocating, where was it? right here, before saving values into a vector, let's say we want to make a vector save values, it's good practice to pre-allocate space for the vector before utilizing it. Pre-allocating essentially means we allow memory to be made for that vector. In MATLAB terms, it means make a vector of all just zeros and then change the zeros to something else as you loop through the vector or as you add values to the vector. So we start by saying vec equals zeros 1 through n, because we see how many elements would you like in your vector. So let's actually simultaneously run this and see what happens. So create vec. How many elements would you like in your vector? Let's say we want 3. So what MATLAB did is it created a new variable vec with just zeros with dimensions 1 row, 3 columns, which is a row vector of 3 zeros. Now as we go through this for loop, every time we enter a new element using input, it's going to be saved in that respective index of the vector. So here the first time we go through, vec of 1 will equal input enter element. So the first one can be 6, enter element, second will be 7, the third will be 8. Here's your very own vector, 6, 7, 8. So that makes sense. What we're going through is every time we go through a loop, instead of vec 1 getting replaced, then it will be vec 2 getting replaced, and vec 3 getting replaced. But all those values were previously stored here. The reason we pre-allocate, the reason we have these zeros be identified here, is because when you're dealing with a lot of values, it is very good practice to pre-allocate, because when you have hundreds of thousands of points in a really big data structure, having to expand upon it each time takes a lot of memory, takes a lot of time. But pre-allocating is very simple and allows for less time to be used when actually running through your code. Now back to using the matrix function. So here I have another function called add_mat, where we add a matrix. So it's very similar to the vector. So in this case, what we're doing is we are going to first get the dimensions of the matrix we want to create, that we want to add, because what we're doing is we're adding all the elements of our matrix. So we're getting the dimensions. We say r comma c equals size of mat. R is the rows, c is the columns. Then we use a nested for loop to loop through the rows and loop through the columns. And inside that second for loop, we say sum equals sum plus, instead of just saying mat or single value, we say mat of I comma j. Because I comma j gives us the index of that specific value we're looking at that point. In the first row, we loop through all of our column values, then we move on to the second row after we're done with all of our columns. So we loop through all those, move on to the third. So if we have a matrix here, so let's say, I'm going to expand this so we can actually see it a little better. So if I say mat equals random, a 5 by 5 matrix of random values, let's say we want the sum of this. So I can say add mat of mat. And that is the total sum of all of 14.49190, etc., etc. So that's how we can use nested for loops for matrix in this case. And then I have just one more example before we're done. So the file earthquake.dat is a data file that consists of various values on the Richter scale of earthquakes in the United States from 2015 to 2019. Calm earthquakes are classified as values less than 4 on the scale. Rough earthquakes are classified as values greater than or equal to 4 and less than 8. Earthquakes greater than or equal to 8 but less than 10 on the Richter scale are classified as dangerous. Use nested for loops to loop through the data and classify all the values, printing off a report that displays the percent of each classification that have occurred in the past 5 years. All right, so this is exactly what we want to get done here. So you can see the best way to do this is actually loop through elements, because if we take a look at the data file, earthquake.dat, this is a data file that created it beforehand. So we have a bunch of values in our data file. We have 5 years for 2015, 16, 17, 18, and 2019. But we have a lot of different values that we have randomly. These are just a lot of different earthquakes that have happened. And we want to classify them as calm, rough, or dangerous. Those are actually not scientific at all. Those are completely made up. Don't use those at all for anything reasonable. That was just made up for purposes of this little demonstration here. So we have our data file. So if you remember, we want to actually load the values. So let's make a script called earthquake class. So we're going to save as earthquake class. So earthquake class. And we're going to say this script will load values from earthquake.dat to analyze the percent of all the different classifications of earthquakes in the past 5 years. So the first thing we're going to want to do is load data file. That's going to be the first thing we're going to want to do in this case. If you remember back when we dealt with file input output, you simply just need to type load earthquake. And when we do this, this is actually going to give us a new variable to use. When we load earthquake.dat, we now have the variable earthquake on our hands that we can actually use in this case. So now we have a new variable. And what we want to do is we want to loop through that variable earthquake and calculate how many calm earthquakes, rough earthquakes, and dangerous earthquakes there were. So that's going to be what we're going to do next. Number of different types of earthquakes. So let's make 3 separate variables because we want to create running totals for all 3 of the different types of variables. We want calm, rough, and dangerous. So these are going to be running totals of all of our different classifications. We have the calm, rough, and dangerous different types of earthquakes here. So now what we want to do is we want to calculate how many of each are in our matrix. And we want to use nested for loops in this case. So we have our matrix saved in earthquake. That's our new variable. So we're going to want to loop through earthquake and pick out what's the value that we have here. So what are we going to loop through in this case? What we're going to need to do first is we need to find the dimensions of our matrix in this case. So we don't know what the dimensions are, so we're going to say r comma c equals size of earthquake, because remember earthquake is the matrix we're dealing with here. R and C will give us the rows, give us the columns, so now we have our dimensions where we can use our nested for loop. So we can say for I equals 1 through R, for J equals 1 through C. So now we're looping through all of these. So what we want to do is every time we get to a new value or we get inside this second for loop, we want to decide what is the classification. And the way we get the classification is by looking at the specific value. So in this case, we have different options depending on what the value is at R comma C in earthquake. Since we have different options we can choose from, we want to use if-else statements in this case. So we can say if, what are we looking at? Well, we're going to look at earthquake at the position R comma C. If earthquake at R comma C is less than 4, let's assume that there's no negative numbers or greater than 10 numbers we got to worry about. So if it is less than 4, we know for a fact that it has to be a calm earthquake, meaning we can say calm equals calm plus 1. Else if earthquake R comma C is less than 8, because remember if it was like 3, it's not going to get here, it's going to get to the first if statement. We can say rough is equal to rough plus 1. Then finally, I could just put else here, but I'm going to just type it out and say else if earthquake R comma C less than or equal to 10, dangerous equals dangerous plus 1. And then we end all of our statements here. So now we have a way to decide what our classifications are and how we can add new earthquakes to all different classifications, to calm, rough, and dangerous. Find total number of earthquakes. So now let's actually find what the total number would be, because remember we need to calculate the fractions or the percentages. We're just going to represent them as fractions in this case, but to do that we have to divide by the total each time. So let's say total is going to equal calm plus rough plus dangerous. That's going to be our total. Now in this case we're going to actually want to print all of them out. So we can say, so let's just say print percentages, let's call them fractions. So first you can say fprintf earthquake classification fractions. Let's call it that. So then we have 3 different ones we want to go through. So we want to say calm. and then we want to put a value in here. Let's go to 3 decimal points. And the value we want to put in here is com divided by total, because remember we're putting a fraction in here. Then we can say f print f rough 0.3 f rough divided by total f dangerous rough divided, no, not rough, dangerous divided by total. And that's all we have to do in this case. So we use for loops in here, iterated for loops, to actually go through, or nested for loops, to go through and actually classify each of the different types. So before we run this, one thing we want to look at is I actually have a little mistake here. We don't want to use R and C because remember R and C are constant values. What we should be using in this case are I and J. We want to put a row value along with our column value. Row value along with column value. Row value along with our column value. So we should be using I and J because those are the values that change. If we leave R and C, it's just going to print the same value every single time, and that's not what we want. If we do this in this case, we can see if we run it, our classifications are as follows. We can see that we have 0.328, 0.446, and 0.226 for each of the different types. So one last little thought I want to look at before I close this video is looking at this script here. So this script actually accomplishes the exact same thing, but it uses, if we see here, this uses 13 lines of code. Let's say we ignore the comments. If we ignore all the different comments we'd have, I'd say we'd have around like 25 lines of code or so. But this is a lot fewer lines, but accomplishes the same thing. As we can see here, we utilized the sum function in MATLAB, and we utilized bitwise operators. And what we did is we created logical matrices in this example here, like earthquake is less than 4 and earthquake is greater than 0. That created a logical matrix that showed all the locations of the COM earthquakes, added all those values together, and gave us the sum of COM, and did the same thing for rough and dangerous. The reason why this is so much shorter is because MATLAB is specifically a language that deals very well with vectors and matrices. That is the biggest perk of MATLAB. So doing something like we did here is actually not the more efficient way to do it. In MATLAB, using a for loop for vectors or matrices generally may not be the most efficient way. Chances are there is a more efficient way to do it using logical operators, bitwise operators, any of these, everything we talked about, logical relational operators, and just combining sums together using different functions that are specific for MATLAB or vectors. That's all I wanted. That was the last thing I want to talk about before I close off. Thank you all so much for watching.